So yeah, these are our names. I'm Alessia and he's Christian. We are both from Queen Mary University. We are PhD researchers. And we work with sound. My background is in architecture and his background is in sound design. So I am interested in space and how space is used and how sound actually is part of this kind of use of the space. And so we'd like to present you some of the projects we are working on, and some we are worked on previously, and some future directions as well. So there's an important component that is the design methodology for this kind of objects, which are very physical, and their way to be played, it really depends by how they are designed and how the sound is designed as well. So we're going to talk about the technology we use for these objects. So the first creation is a broom. So there's an Arduino which is controlling all the input from the sensors on this broom, including an accelerometer and an embedded speaker. And the idea was to create a sensitive object which could interact with the space and was an everyday object which every person could use. But I was mostly interested in how the interaction with the floor and the space could come out of the expressivity of the instrument. So I tested this Mozzi library for real-time audio on Arduino, and later I changed a bit the design of the interaction, including a distance sensor to control the pitch, and some kind of gesture sensing as well. And you can see some examples from the video, hopefully. So there was an FM modulator as well. And so the orientation of the stick of the broom was controlling the frequency of the synthesizer. And after this experiment, I went into trying different time for this instrument. But I was really interested in what people could think if you actually play an instrument like this in a normal house and what can happen. So I had many interesting opinions from my musicians friends, which thought I was a bit crazy. But okay. So after... can you go back to the right one? Okay, so, yeah, I already said that. The second experiment was Odette with Lida Teodoru, and in this case we wanted to experiment with kind of skeleton tracking from Kinect, and we wanted to create an alter ego mirroring a movement of a user. And in this case, the user had to become part of this kind of dialogue, this performative interaction in front of this image. So the participant in this case was becoming the puppet master in a sense, and the shadow created by the object and the lights and also the sound was part of the performance. So when people could come and see this scene, they were thinking, what's going on? And they wanted to be part of this kind of dialogue. And the interesting thing is that the object was kind of fascinating in a sense, but also made by a very common materials as bubble wrap. It was clearly a closed hanger with an Arduino and some servo motors, which also produced sound, which was very creepy. And the sound I decided to program in Super Collider. I used an already existing flute patch, but it was creating kind of different pitch sounds. So when you were waving your arms in the air, then you were creating like spooky sounds, kind of airy. We also have a video to show. What's the next one? So it really seemed like a ghost for everyone.
Funny enough, that's that.
And it was really in terms of understanding how it was working, it was really clear to see all the connection, which was also part of the design of the piece. In this case, in this case, the Kinect was in a black box below the wings. So we used to call them kinetic wings at the beginning. So we were experimenting with kind of responsive structures. And then we decided to play a bit on this kind of personification of the character playing in front of you. You were also animating. And we used OpenNI for the Kinect libraries and processing. So processing was sending serial messages to Arduino. And from this, I will leave
Okay, so I'm going to talk about this one briefly now. So this instrument is called the air harp. So the idea behind the air harp was that it originally started out as a mystery box project. So the idea was that you had a box on the table, and it was all up to the person interacting with the box to figure out how to play this instrument. And I really wanted to design something that allowed the person to make music, pick it up and make music within less than 10 seconds, basically. So this is the way that you interact with the instrument. I'll actually try and give you a live demo first. So basically it's completely embedded, so battery, speakers and all this are in the box. And there are 9 physically modeled strings going across the length of the box. And then there's some physics simulation which changes the position of the string of the object, which in turn plucks the strings based on the orientation of the device. So. So the idea is that the interaction should be very, very natural and very easy to understand. This is also the second generation of the air harp, where we laser cut this nice front panel. The reason we did this actually was to let the sound come out of the box, because initially we just had one single F hole on the front, and that was nowhere near loud enough to amplify the instrument. So here's just quickly how it works. We've got a virtual mass on 2 springs, and as you tilt the box, we can derive the resulting gravity forces that would need to push this mass across the strings. And this is all there is to it, basically. And here's just a picture of the inside. We've got a single accelerometer, a Bella board, which I'll come back to later, a battery and 2 speakers, and a line out, and a potentiometer that does nothing. Okay. I think I just went through all of this. Okay, so physical modeling of sound is really useful for this kind of thing because it does a lot of the work for you. You just tell it, I'm going to put in this much force and it's going to behave exactly how I expect it to within the constraints of this physical simulation. But I found, especially coming from a sound design background, that this is often not enough, and I wanted to be able to perform environmental sound as if I was performing an instrument. So here's a picture of somebody spraying WD-40 on a door hinge, and I say, no, don't do that, because I can use it for making synthesizers. So the idea with this project was to use a trackpad to, like, a very simple input mechanism to produce squeaky door sounds. So there are 2 approaches you can take. You can either physically model the entire system. Here are some papers that use equations derived from tectonic seismic research to produce the sound of friction. I took a different approach to this, which is to kind of approach the sound of a door like a synthesizer, kind of like a modular synthesizer, where instead of thinking about physical processes, you're thinking about oscillators and filters, and you name your parameters according to what you think it sounds like, and it's a bit of a iterative design process. So this is the block diagram of our squeaky door model. We've got an impulse train generator, some amplitude modulation, a bunch of bandpass filters and resonators. And I should say this model was developed based on Andy Farnell's prototype. So I'll just play a video of this. So over here, you can see the trackpad position, the position of my finger as I played it. And here you can see the parameters moving and how they are mapped to the parameters. One more. Okay, I won't play the whole video, but you can look it up later, watch it yourself. Okay, that's the wrong title. Basically, so the model was designed in pure data, and we used touch size from a surface to control the model. And the main thing here is that if you want to perform environmental sound, don't necessarily go for physics simulation, and think about it more like a synthesizer. And I'll just hand over back to Alessia.
So after those experiments you saw before, I decided to start being a serious person and do some kind of soundscape research related to architecture. And so I decided in London to look at the area of Greenwich because of the architecture there and the river and a lot of green. And so I was interested in how a location which is quite known and used as a restorative place by many people, including tourists, could be understood in a different way, just because of its sound. And so I organized a sound walk, which is part of my PhD research, whose updates you can see at this link. And I decided to embed the recordings in an interactive object, and I decided to use fabric for this. The idea behind the fabric is that you can immerse yourself in this situation recorded by someone else, just touching the correspondent buildings. And this is possible because I used conductive thread and an embroidery machine we have, but it can be possible also just doing by hand. And so for every one of these places, I associated one of the recordings I made. So this can be done with Bella, because Bella allows you to detect the touch and also to do some nice fading, which is very natural, and it's what I wanted for this object. Because after the strange sounds coming out of the first two pieces, I wanted something a bit more relaxing to be part of my research. And so in this case, you have the surface of the fabric, which is kind of the conductive part you can touch, and then there's a layer of insulating fabric with some holes, and then the same capacitive part, which is sensing the touch, goes to traces which go to this red ball, MPR 1-to-1, and so I had to stitch all these wires and put them in place there, and everything is going through I2C to Bella. And Chris helped me, programming the code to read these things in real time, but it was amazing that everything could work just by plugging the cables, because the fabric is actually really resistant compared to some other electronics. And so in this case, there's a strong meaning, because I'm trying to look for interfaces that I can bring to other people which are not so familiar with what I'm researching, which is sound and acoustics related to architecture, and try to bring something intuitive to them. And this is also what, like the methodology I've used for another project. So I went to China recently, and we were supposed to create music boxes in a local village. So I was really interested in like the sound, environmental sound there, because it was very relaxing with mountains and river, but also I was interested in the local music. So I decided to record these sounds from local people, and my partner in this project, Yi Shen, she wanted to have these music boxes, very tiny objects projecting shadows, and this shadow was supposed to be the local decoration patterns that they also use in weaving. And so after some research, the project had to be delivered in 7 days, basically. And so I tried to find the easiest way to be able to have local people interacting with these objects and see the reactions. And so I use, in this case, Arduino and Adafruit soundboard and an accelerometer. And so everything had to be embedded in this box, but the interaction should be like really straightforward. And it worked well because even kids could get it easily. I have no sound. So they understood immediately. There was this other feature, you could connect two boxes and play another song just by sensing a magnet. And it was really interesting to go with these boxes in their spaces, in their like social relaxed spaces, just used for gathering and talk about local affairs of a village, and just sleep there or chat and relax. And they were really interested in hearing, of course, their music, and they said, this object is too simple for us. We want our decoration. You have to carve something on the sides, because we don't really recognize this cube as something which is ours. So I needed to be helped by a girl, another design student, explaining what they were saying. And it was interesting to see how different people also were giving different advice on the boxes. So they were saying embroidery is going to be really expensive. You don't have so much money for that amount of time. Yeah, so that's it basically. So you just rotate the side and change the song, and then if you put it back to its original position, then it stops working. So it's really a simple thing, but I thought that in my case, it's important like to do more in the research part, like gathering the right sounds and then leaving the design to the minimum. Okay, then I will go back to the presentation, which is still like somewhere. Yeah. Okay.
Cool. Okay, I'll talk about the lightsaber in a second, but basically while Alessia was doing all this amazing soundscape research, I was in my research group developing this board called Bela, which is an audio platform that works with the BeagleBone, an audio framework really. And this is what we've been using for lots of these projects we've been talking about, basically. So the nice thing about this board is that you've got extremely low latency audio output. So that means if you press a button, it will take you less than 2 milliseconds or less than a millisecond sometimes for the sound to come out of it, which is very fast. And also the sensor bandwidth, the resolution is very high, and the analog sensor sampling rate is very high as well, which is at audio rate. So this allows us to make some very, very objects with a very, very high level of expressivity in the interaction. So to demonstrate this, we built a lightsaber. So you might notice that this lightsaber doesn't look like a lightsaber, it's just a cardboard tube. And this is because we wanted to focus only on the sound. We weren't interested in the lights and so on. So the way this works is we've got a Bela inside one end of the tube and a battery. And these are all the components that we're using. So we've got an accelerometer over here, a piezo disc over here, a speaker, our Billa board, and the battery. So we used a piezo disc to detect hits on the sword. So when you're swinging the sword around and you hit it against a surface, it will go, you know. And as you move it around with the accelerometer, we we integrated the accelerometer value to get a velocity reading, and we used that to produce the iconic lightsaber sounds. And I'll just play a quick video, which I may skip through a little bit, which explains how this works. So the lightsaber is one of the most iconic sound effects. Everybody knows lightsaber from their childhood, and I'm just going to skip forward. Now these delay lines have a variable delay, so okay. So basically, what we did was if I just go back here. Okay, so when Ben Burtt designed the lightsabers, what he did was he played the sound of a TV hum coming through a speaker, and then he used a very long microphone, like a shotgun microphone, and recorded the output as he imitated the swings of the Jedis with their lightsabers in the film. And we replicated this process inside Pure Data. Are you all familiar with Pure Data? For those who aren't, it's basically a digital processing language, a visual language, where you connect lots of components to each other with cables. And we can use this on Billa, basically. So we reproduce this idea of Doppler effects, delay lines, and movement using the PD patch, and then assembled it all inside the lightsaber cardboard tube. Unfortunately, we don't have that one with us to demo today. I'm just going to move straight on to here, which is... I'll just quickly wrap up this, actually. So basically, what we're interested in is how does it feel to interact with a lightsaber when you have this low latency? What would it feel like if you actually had a lightsaber? What would it sound like, and so on? And this is something that was really made possible through the low latency and through the high bandwidth resolution sensor data. Okay, so this is the final instrument we'll show you today, which is we call it the Vangelicizer. Also known as the shaker. And the reason we called it the Vangelicizer was because we wanted to make an instrument that contained literally just an accelerometer, a Billa board, a speaker, and a battery. So something you could hold up. Over here. Something that just requires the most minimal kind of interaction, basically. So So to cut the long story short, basically, we started by making a synthesizer that emulated Vangelis' soundtrack to Blade Runner and the synthesizer settings he had. And then what we did then was we had a very iterative, rapid process of switching between the patch, designing the sound, and designing the sensor mappings to the sound. And because sound and sensor, you don't really distinguish between them when you're programming for a platform like this, it made it very easy to prototype stuff very fast. So basically, what I'm trying to say with this one is that if you have very, very rapid, very iterative design, then you may end up with some strange results, but it will be very, very carefully designed because you've had very, very short iteration steps. Okay, so just to wrap it up, here are some little nuggets of wisdom we thought we'd collected by working on these instruments. So A, keep it simple. There's an enormous amount you can do with just one single sensor. Almost all of these instruments we showed today work with one single sensor or two sensors. And we find that constraints are often extremely useful in making an engaging experience. Also, have this desired experience in your mind when you design the instruments. Obviously, people will misuse it or use it in unexpected ways, but if you've got one design principle in mind, then you'll come up with something very strong. Don't bias the focus just on the sensors or just on the synthesizer, but think of the whole instrument as a whole, and it will help. Otherwise, it's very easy to forget about, how am I going to map the sensor range to this parameter, and actually it doesn't actually sound the way I expected it to, and so forth. And finally, as I said before, make sure you're comfortable with your design and development environment, and make sure you have the ability to have fast iterations. So the more quickly you can see the results of what you're prototyping, the better your results will be. And I think that is all of it from us. Thank you.
Thank you very much. Can I just ask, is the next speaker in the room? Right, okay, if you want to come up, you could ask, if anybody's got one question that they want to ask.
Okay.
This person here.
Hi, when you think about a musical instrument, one of the things about an instrument is predictability. I mean, I know if I do this thing, I will get this response each and every time, and that would enable me to perform and have the same thing happen several times. Most of the things you've shown me seem to be much more like, I don't know what's going to happen. I mean, could this be an instrument that someone could perform and consistently produce a repeated outcome?
Mm-hmm. You want to? Sorry. Okay, so... yeah, the instruments we showed, there was an element of unpredictability, and they were actually designed, some of them, on the principle of I don't know what this thing is, but I want to be able to find out very quickly what it is. Because they're unpredictable in this discovery phase, doesn't mean that they're uncontrollable. It still means that you can learn how to use these instruments. So, for example, the Vangelicizer with a shaker. A few days after we designed it, we realized, we can do this twisty thing, and it sounds like a pizzicato string orchestra, basically. And that is completely repeatable, and the same applies to lots of the other instruments as well. So, I don't know if that answers the question, but basically, if you design it carefully, it will be controllable and repeatable. It may be strange, but it's repeatable, and you can become good at it. So we're going to have these two instruments around if you want to play with them. Otherwise, thank you very much.